Hi there, welcome to yet another episode of Reading with Radio and Antenna. So, we are on chapter 4 of the biography Albert Einstein, and this is the fourth chapter, The Patent Officer. In June of 1902, Einstein was offered a job as a technical expert, third class, at the Bern Patent Office. For an annual salary of 3,500 francs, he was responsible for deciding whether submitted inventions were deserving of patent protection, whether they infringed on existing patents, or whether the products actually worked. Einstein could complete his task so quickly and so well that he had ample spare time in which to pursue his scientific work and was even granted a raise of 400 francs soon after being hired. While living in Bern, Einstein met regularly with a close circle of friends who shared his interest in physics and philosophy. These individuals included the Romanian student Maurice Solvine, his old friend Konrad Habich, an electrical engineer, Lucien Chauvin, and Einstein's closest friend from the Polytechnic, Michel Angelo Besso. These men met late into the night to discuss their intellectual interests and referred to themselves as the Olympia Academy. At the end of 1902, Einstein's father suffered a heart attack and Einstein returned to Milan to visit him. On his deathbed, Hermann Einstein finally consented to Einstein's marriage to Mileva Marek, and the couple wed on January 6, 1903. By this point, Mileva had lost much of her interest in science and had become a housewife. The couple's first son, Hans Albert, was born in May 1904. The years 1903 to 1905 were arguably the most productive years of Einstein's entire career. In 1905, he published three papers that would transform physics in the 20th century. The subjects of these papers were Brownian motion, quantum theory, and special relativity, each of which represented a groundbreaking solution to the most pressing problems facing physicists in Einstein's day. The paper on Brownian motion, entitled On the Movement Demanded by Molecular Kinetic Theory of Particles Suspended in Liquids at Rest, tied in closely with Einstein's dissertation on the statistical molecular theory of liquids. Brownian motion referred to the permanent erratic movement of particles suspended in a liquid, first noticed by the English botanist Robert Brown in 1828. Einstein predicted that the random motions of molecules in a liquid impacting on larger suspended particles, such as bits of pollen, would result in irregular, random motions of the particles. From these particle motion, he then could determine the dimension of the hypothetical molecules causing the motions. This paper, published in the Annalen in 1905, brought Einstein numerous admiring letters from scientists throughout Europe and helped establish his reputation as a significant contributor to physical theory. Einstein's paper on Brownian motion was conservative in its application of statistical methods to the random motion of Newtonian atoms. However, far more revolutionary, Einstein used to term himself, was his paper entitled Concerning a Heuristic Point of View about the Creation and Transformation of Light. In this paper, Einstein argued that under certain circumstances, light behaves not as continuous waves, but rather as discontinuous individual particles called quanta. Einstein was driven to formulate this quantum hypothesis in response to an experimental puzzle that had challenged physicists throughout the 19th century. This motivating puzzle concerned black body radiation, the electromagnetic radiation given off by a hot, glowing coal that absorbs all the light that falls onto it, thus appearing black. This radiation was studied by measuring its spectrum, the amount of energy of any given frequency emitted when the object was heated to a certain temperature. By the end of the 19th century, German experimentalists had studied this spectrum and found that for any given temperature, there was a rapid rise in the intensity of the emitted radiations as the frequency increased, followed by a rapid decline. The characteristic shape of this curve, which was always independent of the type of object being heated, was reproduced theoretically by the physicist Max Planck. However, Planck was unable to explain the shapes of these curves using either statistical mechanics and the corresponding thermodynamics or electromagnetism. The only way for Planck to account for the shape of the curves was by positing that the radiation was emitted in discrete particles called quanta. Planck formulated the equation E is equal to h nu, in which the E emitted by the black body at a given temperature is equal to the frequency of the light involved multiplied by a new universal physical constant soon named Planck's constant h. However, Planck did not realize the ramifications of his own formula, viewing it as nothing more than a mathematical device to explain the radiation curve. It was Einstein in 1905 who explained Planck's law as a fundamental statement about the nature of light and its interactions with matter. In his 1905 paper, Einstein demonstrated that light could only be emitted or absorbed in finite discrete units. This idea challenged the standard physical theory of the time, according to which light was a continuous wave. In the 1860s and 1870s, James Clerk Maxwell had shown that light is a wave of electric and magnetic fields and that atoms absorbed or emitted light waves in a continuous fashion. However, Einstein showed that the continuous waves of Maxwell's equation could be considered only averages over the light quanta emitted or absorbed. Einstein used his light quantum hypothesis to explain another important puzzle, the photoelectric effect. This phenomena involves the ejection of electrons from a metal irradiated by light. In the experiment, light of various frequencies is shown on the metal. Once a certain threshold frequency is reached, the metal ejects electrons in response. The energy of these electrons rises linearly in a curve with the frequency of the incident light. The resulting curve is independent of the intensity of the incident light. These results could not be explained according to traditional wave theory because, according to this view, the energy of the light is proportional to its intensity. So, the energy emitted to the ejected electrons should be proportional to intensity rather than frequency. Moreover, according to the traditional view, there should not be a threshold frequency needed to eject the electrons. A bright enough light of low frequency should be enough to eject electrons. Okay, now they have been replaced. Now here is antenna and here is radio. And let's continue. However, Einstein explained that if light is considered as composed of discrete particles, later called photons, then each photon would carry a definite amount of energy that was then imparted to the ejected electron. However, the energy of an incoming photon would have to be great enough to eject an electron in the first place, resulting in a frequency threshold. Thus, Einstein was able to provide a theoretical explanation for the energy versus frequency graph of the photoelectric effect. When Einstein first introduced his photon idea in 1905, he called it merely a heuristic that was useful in explaining the photoelectric effect. He emphasized that while some phenomena required particular interpretation, many could still be explained using the wave interpretation. However, in a series of subsequent papers published in 1906 and 1907, Einstein used his statistical mechanics to propose the existence of light quanta. For the rest of his scientific career, he explored the significance of the resulting wave-particle duality in terms of his search for a fusion or unity of the wave and particle aspects of the electromagnetism. First, however, he published another great 1905 paper. Hey, can you guess what that 1905 paper is? Come. Come. Can you guess what that 1905 paper is? Which is the subject for the next chapter? So he has run away somewhere. Can you guess? He's obedient. He's very obedient. He is very naughty, very naughty. Come. Oh, come. So, next chapter is Theory of Relativity Waiting, but that is the chapter for the next day. Good night.